Okay. I'm gonna get started. Um, so, quick announcements. Worksheets 8 through 12 and homework number 2 are due on the 7th. That is Tuesday next week. We're gonna finish chapter 12 today, so you'll have some time to finish that up. Test number 2 on chapter 8 through 12 will also be Tuesday next week. It's gonna be 60 questions, multiple choice, like the last test. You get one sheet of notes, double-sided, to use on it, and it's gonna be in class. It's gonna be basically the same as the last test. And yeah, that was all the announcements that needed to happen. Okay. So let's continue on. We covered the large moons of the solar system. Let's move on to medium moons. So again, that number is out of date. There's a whole lot more than 170 moons. But I mean, they just a few months ago released an extra 100 plus around Saturn. So but there are only 3 in the inner solar system. There are 6 large moons. There's a large number of medium moons. And there's a bunch of small moons that are probably captured by us. So these are the medium-sized moons, some medium-sized moons in the outer solar system. Their densities suggest that they are rock and water ice. So these are some of the medium moons of Saturn: Mimas, Enceladus, Titus, Dione, Rhea, and Pegasus. And some of the medium moons of Uranus: Miranda, Ariel, Umbriel, Titania, and Oberon. And Proteus is one of the medium moons of Neptune. Jupiter also has some medium moons that are not on this particular list. So the medium moons of Jupiter are Amethyla, which is about 200 kilometers across. It was discovered in 1892. It's the last satellite to be discovered visually. Everyone after that was discovered via other techniques. It has a bright surface and it's heavily cratered. This is probably sulfur from Io, and its surface is old and inactive. And then there's Himalaya, which is 170 kilometers across, and it's not yet been closely studied by spacecraft, so we don't know a lot about it. Here are some of the moons of Saturn in natural color. We have Earth's moon, Apagus, Mimas, Enceladus, Titus, Rhea, Dione. So Mimas has a large crater. They're all pretty similar looking. They're all balls of rock and ice. Mimas is 400 kilometers across. It's heavily cratered. It has a large impact. It is the so-called Death Star moon. Enceladus has an icy surface. It has a mixture of young and old terrain, and it has subsurface water. There are plumes of water erupting from the south polar surface that we've sampled, and they are feeding into one of the small rings of Saturn. So here is a video about the water on Enceladus.
Recently, Cassini has found that a tiny moon that orbits around Saturn has jets and plumes of water coming out of it. These particles go out and they form the E-ring. And in flying through the E-ring, one of the instruments on Cassini, the Cosmic Dust Analyzer, can take those particles and get a composition. And as part of that, they see salt.
This is salt, and this is what we found in the ice particles we detected in Saturn's E-ring. And what we think is that the salt comes from an ocean below the surface of the moon Enceladus. The sodium is a tracer for a subsurface ocean. That's the material of the ice particles, kind of in water, like on Earth.
And that salty ocean tells us something about what might be going on inside of Enceladus to create the jets and plumes that you need. Water, liquid water, in contact with the rocky core to get out the sodium. You could sort of think of maybe the plumes of maybe sort of the breath of Enceladus, you know, coming out and telling us something about its interior.
So what we can say is we have a reservoir of liquid water, and liquid water is one of the preconditions for forming life.
I was surprised and also very excited to find out that, you know, we're getting closer and closer to the conclusion that you have liquid water, possibly a liquid ocean, on a moon that's so tiny, and in a place where we didn't expect to find conditions where you might find life. This tiny moon, just 300 miles across, that might have liquid water and the conditions, the precursors for life. The focus, as Cassini continues in its Equinox mission and continues on into the future, will be to have more close flybys of Enceladus, to fly through that plume, fly close to this tiny moon to learn more about the processes going on inside.
So continuing on, Tyson is about 1,000 kilometers across. It's icy and cratered with lots of faults covering its surface. Leo is about 1,100 kilometers across. It's icy. It probably also has a subsurface ocean. Rio is 1,500 kilometers across. It's one of the biggest moons on Saturn. It has a heavily cratered surface. And Epetus is 1,400 kilometers across. It has light and dark halves. So one side is light, the other is dark in color. Here are some of the moons of Uranus and Neptune. These are the moons of Uranus with Oberon, Miranda, Ariel, Umbriel, and Titania. So Uranus is somewhat unique in having moons named not after Greek deities, but after, well, characters from English literature. These are from Shakespeare. These are fairies from Shakespeare plays. And then Neptune has a moon, Proteus. So Miranda is the smallest of the 5 major Uranian satellites, but it's very interesting. It's mostly water ice, but it's very interesting because it's incredibly irregular and jagged. It looks like it was broken apart and put back together, roughly. There's signs of intense geological activity. So, you know, Miranda shows evidence of this violent past, though the origin of the surface features is unknown. But it's very jagged and irregular. Ariel here has active ice geology. The surface is being, you know, you're getting resurfacing going on. There are tectonic cracks and icy flows coming from the interior. Umbriel has an icy surface. It's the darkest, and it's heavily cratered, but it is the darkest surface of any of the Uranian moons, hence the name Umbriel, which implies darkness. Titania is the largest at 15 kilometers across, is the largest moon of Uranus. It has signs of both impacts and icy volcanoes. And Oberon is the second largest. Is also about 15 kilometers across. Titania and Oberon are both about the same size. It has a dark reddish surface and seems to be shaped primarily by impacts. Neptune has a couple of medium moons. There's Nereid, which is 170 kilometers across, has a highly eccentric orbit. And Proteus, which is heavily cratered and probably did not form with Neptune. So Neptune seems to have captured more of its larger moons. So when it comes to the medium moons, how were these formed? To our understanding, the majority of the large moons formed with the planet. They're big enough that some process involved forming with the planet, with probably the exception of Triton around Neptune. The small moons were likely captured because they're dinky. They just are various space rocks that got close enough to get grabbed. The medium moons are probably a mix. Some were formed with the planet, some were captured. It probably varies a bit. They are quite a bit smaller, so they could be captured objects, but they're also large enough that they could be formed with the planet. So, one of the questions you might ask is, why are Jovian moons more geologically active than small rocky planets? Like, look at Miranda here. It's got crazy cliffs and stuff. Well, part of this is that it takes more energy to drive geology in a rocky planet than in an icy moon. So rock melts at higher temperatures, while ice melts at lower temperatures. Only large rocky planets will have enough heat for geological activity because of that, while tidal heating can melt the internal ice of a Jovian moon and drive activity. So in order to have geology on the terrestrial planet, you need internal heat, primarily from radioactive decay, or remaining heat from differentiation can cause volcanic and tectonic activity. Only large planets retain enough internal heat to stay geologically active. Smaller planets cool off faster, so they've lost their internal heat. For an example, Mars probably retains some internal heat. If it had been smaller like Mercury, it would probably be completely geologically dead today. If it had been larger like Earth, it would probably have more active and more ongoing tectonics and volcanism. So, well, here we have a Jovian moon. So Jovian moons can get additional heat from tidal heating. Tidal heating can cause tremendous geological activity on moons with elliptical orbits around massive planets. And even without tidal heating, icy materials can melt and deform at much lower temperatures than rock, increasing the likelihood of geological activity. And together, these effects explain why icy moons are much more likely to have ongoing geological activity than rocky terrestrial worlds of the same size. For example, here, Ganymede shows evidence of recent geological activity, even though it's similar in size to the geologically dead terrestrial planet Mercury. So the medium moons of the outer solar system show a varied distribution of surface features. Some of them are heavily cratered, others show signs of geological activity. Some may have been captured like many of the smaller moons have been. So let's talk about things that aren't moons. We talked about the planets. We talked about the moons around the planets. Let's talk about other stuff in orbit around the sun. We're going to start with the bigger things, Pluto and the dwarf planets. So there are two big rings of stuff, concentrated stuff around the sun. There's rocky stuff closer to the sun in the asteroid belt, and there's icy stuff out further from the sun in the Kuiper belt. Pluto and most of the dwarf planets are in the Kuiper belt, except for Ceres, which is in the asteroid belt. So this is a short video about small bodies, classifying small bodies. They can be asteroids, they can be comets, they can be dwarf planets. Primarily, asteroids are rocky, comets are icy, dwarf planets are anything big enough that they can pull themselves into a ball and are orbiting the sun. But they're not big enough to dominate their orbit like the actual planets do.
Welcome to an overview of the chapter titled Asteroids, Comets, and Dwarf Planets. In this video, we'll introduce a few of the chapter's key learning objectives. In particular, we'll describe the classification and importance of the small bodies of our solar system, explain why there is an asteroid belt, explain why comets are found in two general regions, and discuss the nature of Pluto as revealed by New Horizons. In earlier chapters, we identified the fact that the Sun is orbited by vast numbers of small bodies known as asteroids and comets as one of the four major features of our solar system. Small bodies may seem insignificant, but they have had profound impacts on our existence. For example, recall that Earth formed inside the solar system's frost line, where only rock and metal could condense into solid form. We therefore presume that our planet's water and most of its atmospheric gas must have been brought in by ice-containing asteroids or comets. Asteroids and comets are also responsible for the impact craters found throughout the solar system, including on Earth. One such impact has been tied to the extinction of the dinosaurs, an event that paved the way for our own existence. Despite these deep connections, we only occasionally notice the small bodies in our everyday lives. For example, we see a comet in the night sky only on relatively rare occasions, which is probably why comets have long evoked superstitious beliefs. More commonly, we see specks of comet dust burning up in our atmosphere as meteors. You can see a few meteors on almost any clear night, and more during one of the major annual meteor showers, each tied to dust tracing out a comet's orbit. On rare occasions, an object large enough to avoid burning up completely falls to the ground, where we may find it as the rock type we call a meteorite. The wide range of sizes and compositions for small bodies makes it a challenge to classify them, but in general, we do so as follows. Asteroids are small bodies made primarily of rock or metal, implying that they formed in the inner regions of the solar system. This montage shows asteroids that have been visited by spacecraft to scale, and in comparison to our moon at the top. Comets are small bodies that contain significant amounts of ice, implying that they formed in the cold outer regions of the solar system. These images show a comet photographed by the Rosetta spacecraft. Note that comets like this one, which visit the inner solar system and grow visible tails, are rare interlopers. The vast majority of comets never come close enough to the Sun for any of their ices to vaporize. The biggest classification challenge comes from the largest of the small bodies, shown here in a montage of photos and artist conceptions to scale with Earth at the bottom. Note that while all are much smaller than Earth or even our moon, some have moons of their own, and a few, including Pluto, Eris, and Ceres, are large enough for their own gravity to make them round in shape, which is the criterion that classifies them as dwarf planets. Two other objects are also currently classified as dwarf planets, though our solar system may have a few dozen other large asteroids and comets that may also meet the dwarf planet definition.
So, asteroids are rocky inner solar system remnants. Asteroids leave trails in long exposure planet images because of their orbital motion around the sun. We try and track near Earth asteroids because those are the ones that might run into us, and that would be bad. And we do have ideas on how to actually adjust the orbit of an asteroid if we have enough warning. But comets are icy outer solar system remnants. So comets spend most of the time far away from the sun. if they do come close to the sun, they do get a spectacular appearance where you get a glowing head and a trail of material being blown away from the sun by the solar wind and the light of the sun actually pushing on the gas and dust. And then a meteor is the flash of light produced as a small object enters the atmosphere, and a meteorite is an object that actually survives the trip through the atmosphere and ends up on the ground. And it's quite possible to find like tiny specks of meteorite dust all over the place. But it's hard because they're literally like microscopic, and there's only like a few per square meter. So then when people want to figure out how much like meteorite dust makes it to Earth, they go to Antarctica and measure where there's not much else there to get in the way. Because it's hard to tell the difference between meteorite dust and stuff artificially produced by humans. So dwarf bodies are small bodies that are large enough to be round, and the discovery of Eris in around 2006 led to a debate about the definitions and the eventual adoption of the dwarf planet category in 2006. It was a bit earlier that they discovered Eris. And most of the dwarf planets we know of are in the Kuiper Belt. So Pluto and the Kuiper Belt. The Kuiper Belt is this ring of comets out beyond.
In contrast, the Kuiper Belt comets probably still reside in the region in which they formed, beyond the orbit of Neptune. This allowed a few of them to grow to relatively large sizes, which brings us to the final topic of this video, Pluto, one of the two largest known members of the Kuiper Belt. Pluto was discovered in 1930, and while we learned more about it over time, even the Hubble Space Telescope could reveal only vague surface features. Then, in 2015, the New Horizons spacecraft flew past Pluto, allowing us to see this world in fantastic detail. Despite Pluto's small size, New Horizons images show that it has had recent and may have ongoing geological activity. Pluto even has a thin, hazy atmosphere revealed in this view looking back toward the Sun. To recap, in this video we have described the classification and importance of the small bodies of our solar system, explained why there is an asteroid belt, explained why comets are found in two general regions, and discussed the nature of Pluto as revealed by New Horizons. I hope this will help prepare you for your follow-up reading and class time, and suggest that you follow the...
So, let's talk about Pluto. The big question that was on everyone's mind is Pluto a planet? Well, it's a lot smaller than the 8 major planets. It's not a gas giant like the outer planets, but it's way out in their range. It has an icy composition like a comet, and it has a very elliptical inclined orbit. So it has a lot more in common with comets than with the 8 major planets. It's just relatively large for a body out in the Kuiper Belt. So what a planet was not formally defined until 2006. Now there's a planet, or a major planet is defined by doing these 3 things. It must orbit the sun. It must be massive enough to pull itself into a spherical or ellipsoidal shape. And it must be able to clear its orbit of debris or dominate its orbit. There's a lot of debate about the precise definition of this, but just as reference, if you took all the other stuff in Earth's orbit and compared it to the mass of Earth, it would be a few percent of the mass of Earth. If you took all the other stuff in Pluto's orbit and compared it to the mass of Pluto, ignoring Neptune, but all the other stuff, it's 20 times the mass of Pluto. That's why Pluto is not a planet anymore. But we discovered a number of large objects in the Kuiper Belt that were dominating the orbit, and this necessitated the change. Basically, what happened is we started finding more objects out in the Kuiper Belt, and we're like, these are all kind of like Pluto. And then we found Eris. And the reason Eris was a big deal is because it's more massive than Pluto. And this isn't the first time a planet has ceased to be a planet. When the asteroids started to be discovered, they were called new planets. So Ceres was a planet, and then a few other asteroids were planets. And then eventually they realized there were a ton of these things all in a belt, and decided that they were now asteroids in the asteroid belt. So the general definition is that now a major planet has to meet these conditions. So for Pluto, it orbits the sun. It's massive enough to pull itself into a spherical or ellipsoidal shape, but it is not able to clear its orbit of debris. So if it meets the first two and is not a moon, this is a new classification of a dwarf planet. So there are 5 official dwarf planets. There are about half a dozen or more possible dwarf planets that haven't been made official, because basically they just haven't had the meeting to update. And then there's some, it's hard to get all the data needed to make it strictly official, but there's plenty of really solid candidates that are almost certainly dwarf planets. We just don't have, as solid imaging as we would like. So, the 5 official dwarf planets, they are Ceres, which was discovered in 1801. It's the only dwarf planet in the asteroid belt. Pluto, which was discovered in 1930 and visited by the New Horizons spacecraft in 2015, which did a flyby. Basically flew between Pluto and Charon. I think it was basically between, and took a lot of pictures. It couldn't stop because it's going much too fast. And then it also imaged some other Kuiper Belt objects after it passed Pluto. Haumea, which was discovered in 2004. It's not perfectly round, it's ellipsoidal, it has 2 moons. Eris, which was found in 2005. And the big thing about Eris is that it's a little smaller in diameter than Pluto, but it's more massive than Pluto. So it's about the same size as Pluto, so it's hard to discount. And then lastly, Makemake, which was also found in 2005. And Haumea and Makemake are a little sketchier in their data for them being dwarf planets. We have much better data on the others. So Ceres is the largest object in the asteroid belt. It has a diameter of 950 kilometers. It was studied by the Dawn spacecraft. It was discovered in 1801 and was originally thought to be a new planet. As were the next few asteroids discovered. Eventually they found enough that they reclassified them as asteroids. So it was reclassified as an asteroid, and it is now classified as a dwarf planet. It's in the asteroid belt. It's the largest object in the asteroid belt. And as far as we know, it's the only one big enough to turn itself round. So it's the only dwarf planet in the asteroid belt. Pluto was discovered in 1930 by Clive Tombaugh. He was searching for a planet disturbing the orbit of Neptune. There's some debate whether Pluto was actually disturbing the orbit of Neptune or he was just looking at noise, but he found the planet anyways. Pluto cannot be imaged clearly from Earth. So this is, Pluto from Earth. It's a bright dot. Now, Hubble gave us views of light and dark colored terrain. And we got much better imaging when New Horizons actually flew past it and took pictures of the surface. So here's an actual image of the surface of Pluto from New Horizons. So Pluto is an icy planet. It's covered with ice. Its orbit is tilted and significantly elliptical. It's significantly more tilted than any of the other major planets. Um, and it does pass through Neptune's orbit, but it is in resonance with Neptune's orbit. So Neptune orbits 3 times during the time Pluto orbits twice. And so this resonance prevents a collision. For every 3 orbits of Neptune, Pluto orbits twice, and that means they're never in the same place at the same time. So Pluto, as its largest moon, Charon, is like half the size of Pluto. It's really big compared to it. This means it was probably made by a major impact. We think probably what happened is there's one big body that got broken in 2. They're tidally locked to each other, so they always have the same side facing each other as they orbit. Pluto is very cold. It's about 40 Kelvin, so that's negative 233 degrees Celsius. And it has a thin nitrogen atmosphere that will refreeze onto the surface as its orbit takes it further from the sun. So Pluto's surface has like frozen nitrogen on the surface. And New Horizons has revealed a geologically active surface with mountains made of ice and far fewer craters than expected. There's thought that there's like various different forms of ice on the surface of Pluto. There's frozen nitrogen on the surface, things like that. It's actually fairly interesting looking. And before New Horizons, we knew that Pluto had 5 moons. So there's Pluto and Charon, which are tightly locked to each other, and then it has 4 small moons. Styx, Nix, Kerberos, and Hydra, going from the inside out. And it was discovered in 1930. It was thought that it was needed to explain irregularities in the orbit of Neptune and Uranus. It turns out that there weren't actually any irregularities there, or they were, Pluto didn't actually explain these irregularities. It's kind of just lucky. But it was discovered in 1930. And over time, we've got a more detailed view. So, here's our original Lowell Observatory observation of Pluto. It's just a dot. Here's 2010. So this is from 1930. This is from 2010, the Hubble Space Telescope. And here's 2015 from the flyby of New Horizons. It's sort of pinkish, covered in sheets of ice with some interesting properties. So it's got much more active geology than previously expected. So here are some mountains that are as tall as the Rockies, probably made of water ice. There's flowing nitrogen ice, even above 40 degrees above absolute zero. And that is pretty cold for nitrogen. I don't think about solid nitrogen ever. Liquid nitrogen at atmospheric pressure is at 77 degrees above absolute zero, but I don't remember where it freezes. So Pluto, New Horizons in 2015, image the surface. It has an icy surface, much like the large moons of the outer planets. There are ices of methane, nitrogen. The light areas on the surface are frozen nitrogen, and very few craters. The darker areas are more cratered. And a variety of different types of terrain were viewed on the surface. So here are some examples. This is the Voyager Terra, there's the Sputnik Platina, the Hayabusa Terra. You can see there's various different surfaces in different areas. And these are some of the names of various objects. So these are sort of the methane ices, the lighter areas. You can see the darker areas are more irregular. Here you can see some of the variety of terrain. So we could have these flat plains, these blocky mountainous areas, and these cratered islands. And here is a flyover of the surface of Pluto. Yeah, turns out this bug is only on this computer. So I'll try and, you know what? No, I'll see if I can restart it and fix it, but I don't know what that problem is. Oh. So we have hummocky cratered uplands, washboard terrain, chaotic blocky mountains, and then these cellular nitrogen ice plains, these are plains of ice, nitrogen ice that form these big cells. And then we get to more of the regular nitrogen ice plains in a little bit. But these last for a while. It's the scale there, 10 miles across. Yeah, now we have these non-cellular, not organized into the cells, just sort of continuous nitrogen ice plains. And then pitted hummocky nitrogen ice plains. And rugged dark highlands. So you can see there's quite a bit of variety in terrain, and that's just a strip across the surface. So it has a thin atmosphere of nitrogen gas that you can see here. This is Ch12, its large moon, which was discovered in 1978. It's half the diameter of Pluto. When it was imaged by New Horizons, it has a very similar surface to Pluto. And it's tidally locked to Pluto, and Pluto is tidally locked to Ch12. They're constantly facing each other. And 4 smaller moons have been discovered as well. So the surface of Ch12 also shows evidence of recent geological activity. So the smooth regions resemble the lunar mares, suggesting the eruption of lava, which in this case would probably be water. And then there's rough areas of impacts. And here are the small moons: Styx, Nix, Kerberos, and Hydra above Ch12. So Pluto's moon Charon was discovered in 1978. It's orbitally locked to Pluto. It's about 1/6 as large. It's half the diameter, but about 1/6 is the mass. Pluto also has 4 smaller moons: Nix, Hydra, Styx, and Kerberos. And here is a video showing the orbits of those moons and how they sort of tumble chaotic. So Charon and Pluto orbit their mutual center of mass here. And because they're irregularly shaped, they give kicks to the other moons and cause them to tumble irregularly in a chaotic motion in the strict sense. Chaos, no, as in chaos theory. And Charon's orbit is at a weird angle as well. It's at 118 degrees to the plane of Pluto's orbit. So unlike most other moons, which orbit in the same plane as what they're orbiting orbits the planet. Charon is sort of weird tilted angle. That probably is more evidence from the fact that it formed from a strange impact. Though it is closer to Pluto's rotational axis. So other Kuiper belt comets. So the Kuiper belt extends from about 30-ish to about 50-ish AU. It could, so from Neptune's orbit out to about 50 AU, we think. It contains about 100,000 comets, more than 100 kilometers across. The comets all orbit roughly in the same plane and direction as the other planets. And then beyond the Kuiper belt, there is the Oort cloud, which extends out to about 50,000 AU, much bigger, and contains about 1 trillion comets. But the comets in the Oort cloud all have random orbits and tilts and eccentricities. They're all sort of, they form like a big ball around the solar system. So we don't know much about other Kuiper belt comets and objects. Their composition is expected to be similar to Pluto. In 2019, New Horizons continued on and visited another Kuiper belt object, a small, vaguely snowman-shaped comet. It's basically two balls stuck to each other, so it does kind of look like a snowman. Here is Erotica. So you can see it's vaguely snowman-shaped. It's two round things glommed together. It's a relatively small object, but it was along the path New Horizons was taking. So we could continue the image. Because New Horizons is just flying off. It doesn't have any way to slow down. So let's go over some of the other dwarf planets. Eris is comparable in Pluto to size. It is known to have a moon called Dysnomia. So this is an image of Eris. There's Dysnomia orbiting about Eris. So that's part of how we know the mass of Eris. So the first Kuiper belt objects were observed in the 1990s, and more than 1,200 are known now, and some of them are comparable in size to Pluto. And the reason Eris was a big deal is because it's more massive than Pluto. So this is Eris and its moon Dysnomia. This is Haumea. This is an artist's conception. Haumea is not spherical, it's ellipsoidal. It has two small moons, it has two moons. It was discovered in Hawaii, so by a Hawaiian telescope. So it's named after Hawaiian deity. As is Makemake. This is an artist's conceptual image of Makemake. And both Haumea and Makemake were declared to be dwarf planets based on their reflectivity. It's a little complicated, but the way they figured out that they were dwarf planets and that they were actually round wasn't as solid as the others. And here's some of the largest known trans-Canadian objects, generally called Pluto. Several of these are considered to be dwarf planets. So several of these have been called dwarf planets in papers and stuff, but haven't been declared officially so by the International Astronomical Union, basically because they haven't had another meeting to add more to the list. So these are, Pluto, Eris, Makemake, and Haumea. Those are the official dwarf planets, and then there's things like Quar, Salacia, Orcus, Sedna, 2007 OR10, 2002 MS4. When they have a name like that, they were found in a survey. They were basically numbered. So this is date. The letters probably indicate the survey, and then the number probably indicates the object that was found. And they just haven't been given names yet. There's a few others. There's Gong Gong. I like Gong Gong's name. So in 2006, a planet was defined. Pluto was removed from the planet classification and reclassified as a dwarf planet. 5 official dwarf planets are known. 2 of these have been explored by spacecraft. Let me see if I can quickly look up how many claimed dwarf planets there are. The list of possible dwarf planets. So this something like 1,000 possible dwarf planets. There's a table on Wikipedia if you want to look it up. So we talked about various objects floating around, also orbiting the sun. We talked about moons around the outer planets. Let's talk about the other thing that all the outer planets have that we haven't discussed yet: rings. All the outer planets have rings. The most dramatic set of them is the rings around Saturn. The ring system of Saturn is quite large and complicated and can be easily seen from Earth. But all the other Jovian planets also have rings. They just aren't anywhere near as impressive as Saturn's rings. So the rings around Jovian planets, all of them have rings. They seem to also be tied to the moons. They're related to the moons.
Jovian planet systems also have a third major component after the planets and their moons, which is their ring systems. Here, we see the spectacular rings of Saturn, along with an added bonus. This small blue dot is Earth, visible far in the distance. Although the rings may look fairly solid, they are actually composed of countless icy particles, as illustrated in this artist's conception of what they would look like up close. In fact, all 4 Jovian planets have rings, though none of the others are nearly as photogenic as those of Saturn. As you continue your study, you'll learn why rings are thought to exist. To recap, in this video, we have discussed basic similarities and differences among the Jovian planets of our solar system.
So all 4 of the Jovian planets have a ring system. All of these ring systems have some significant differences. So here's Saturn's impressive. Jupiter's is basically a band of dust, which is why in that image it was, it's hard to see. Saturn's are the most visible and they're highly reflective. Uranus's are very, very narrow and they're made of darker material than Saturn's. So Saturn's are made of basic ice mostly. They're highly reflective. They're light in color. Uranus's are dark. They're like soot or coal. And they're very narrow. And Neptune's are similarly dark, but also have gaps in the rings. So the rings are made of billions of tiny particles orbiting the planet. They're basically a bunch of tiny materials orbiting the planet. And the ring particles interact with each other. They gravitationally attract each other. They collide with each other. It's thought they might be a shattered moon. It might be that if a moon had a massive collision and shattered into tiny pieces, that would form a ring. And you could form the ring particles. And a body that's too close to the planet can actually get torn apart by tidal forces. And if we look, most of the ring systems are within that limit where a body would get torn apart by tidal forces. So it may have been that a body close to the planet was torn apart or prevented from forming by tidal forces from the planet. The rings are not solid. They're composed of small, rocky, and icy particles. Here are some of the rings of Saturn. They have inner and outer radii here. So the innermost ring is the D ring, from about 1 times the one planet radius to about 1.23 planet radius. It's about 1,400 kilometers across. Next, there's the C ring, from about 1.23 to about 1.53 planet radii. It's about 1,800 kilometers across. Then there's the B ring, 1.53 to 1.96. It's about 25,600 kilometers across. Then there's the A ring, from about 2.04 to 2.28 kilometers across. Notice there's a significant gap between the A and B ring. That's called the Cassini division. And it's about 14,600 kilometers across. So the B ring is the widest. So what it was, they laid the rings from the outside in, A, B, C, D, and then they later found E and F rings, which are much smaller and fainter. So the E ring goes from about 3.5 to about 5 kilometers across, which is 90,000 kilometers wide, but it's very faint. The F ring, so this is actually the biggest, but it's very faint. And the F ring is very thin, at only 100 kilometers across. And it seems to be fed by Enceladus, actually. So the rope limit is where the tidal forces of a planet are too strong for a moon to survive. And this is where rings are formed. Something similar is likely to happen to one of the moons of Mars. It's actually within the rope limit. So it's potentially thin. So if something enters the rope limit, it can get seriously distorted by tidal action, torn apart, and could become part of the ring. And all observed ring systems are within this limit. So here's the rope limit. Here's Jupiter's faint dusty ring. Here's Saturn's ring system with the Cassini division. Here's the F ring. I guess the E ring is outside, but there's very little is outside. Here are Uranus's rings. You can see they're quite thin. And here are Neptune's rings. You can see they're all within the rope limit. Approximately. Jupiter has a small, thin ring. It's very dusty. It's hard to see. It was discovered in 1979 by Voyager 1 when Voyager visited Jupiter. It has very faint, dusty rings made of very small particles. It's best seen in scattered light with scattered light lit from behind. So to do that, you need to be beyond Jupiter, which is very hard to do for Earth. Saturn's rings. These are Saturn's rings. They're the most obvious rings. The rings look like large concentric sheets. There's this dark gap that's called the Cassini division. If you look at it more closely from spacecraft, there's lots of tiny individual rings separated by narrow gaps. It turns out all the gaps, most of the gaps are tied to moons in some way. And this is an artist's conception of the particles in a ring system. The particles will clump together because of gravity, but small random velocities can cause collisions to break them up. So there has to be some force that helps keep the ring stable. Otherwise, basically collisions and things running into each other would just sort of slowly disperse these rings. And that seems to be caused by moons. So Saturn's rings were seen by Galileo, but weren't recognized as rings. He just saw lumps on the side of Saturn because his telescope was small and not that great. They were recognized by Huygens in the 1650s. Cassini recognized that there were distinct rings and gaps in between, hence the Cassini division, and why the probe around Saturn is called the Cassini probe. The largest of these is called the Cassini division. It's between the A and B rings. So these are some of the rings. Here's the A and B, there's the Cassini division.
From a large distance, Saturn's rings look like a solid disk of material surrounding the planet. As we zoom in, we find this disk is made up of many individual rings, each separated from the next by a narrow gap. If we could wander into the rings, we'd find that they are actually made of countless icy particles, ranging in size from dust grains to large boulders.
So, and we can see different views of Saturn's rings as the planet moves in its orbit, because Saturn, like Earth, is tilted. So sometimes the top of Saturn, sometimes the North Pole of Saturn is facing us, sometimes we see the side, sometimes the South Pole is facing us. So when one of the poles is facing us, we can see more of the rings. When it's on the side, they're more edge on. And we can see the gaps of rings, all these many individual rings separated by narrow gaps. So these rings are extremely wide and thin. If they were the same scale as a piece of paper, they would be thinner than a piece of paper. They're designated by letters. The A, B, and C rings were the widest and first discovered, then the D. The F ring is very narrow. The E ring is very faint. And there are multiple ringlets within each ring. So each ring is a bunch of tiny little rings. And Voyager probes showed Saturn rings to be much more complex than was originally thought. And here is Earth on the same scale as Saturn's rings. And so here you can see the multiple ringlets within each ring. So this is like in the middle of one of the rings. There's lots of tiny little individual ringlets. Some of the gaps we see in rings are caused by tiny moons that are orbiting in those rings. They clear out a gap. They actually hold together rings, or tightly you can have what are called shepherd moons, where a couple of moons on either side of a ring keep that ring from drifting apart. So gravity from the moon will nudge some faster and some slower, and basically it will widen that gap. So the 8-kilometer wide moon dampness clears the gap of the rings here. And you can see the distortion from its gravity. Here are some shepherd moons in Saturn's F ring. So Saturn's F ring is kept so thin and tight because of these shepherd moons that basically, as they orbit, pull the ring tighter together. The gravity of both of these moons pulls the ring in tighter and keeps it from drifting wider and apart. But the larger rings are actually held together by resonance with the bigger moons. So the rings of Saturn are primarily made of water ice. They're highly reflective. And the size of the particles vary from basically dust up to about 1 meter in size. The rings of Uranus were discovered in 1977 when they occulted a star. So there was the flying infrared telescope was observing Uranus, and Uranus passed in front of a star. And interestingly, the star blinked out in a pattern. Then Uranus occulted it, and then that same pattern in reverse repeated on the other side of Uranus. So the light from the star dimmed multiple times, and then that repeated after occultation in the reverse order. This confirmed rings, because we saw the same pattern on either side. And the rings of Uranus are very narrow compared to Saturn's. They're confined by shepherding satellites, and they're much darker. So the rings of Uranus were originally imaged with an infrared telescope on an airplane. It has 9 thin rings. The inset up here, this is the epsilon ring. They're named with Greek letters and numbers. A mixture, because, of course. Here are the two shepherding moons that keep the epsilon ring of Uranus from diffusing away. Particles of Uranus's rings are very dark. They're as dark as coal. They're probably carbon or hydrocarbon compounds. They're actually probably relatively, they're carbon rich, so, similar, and they're better seen in forward standard light, looking back towards the sun. So again, rings that are easier to see when you're beyond the planet, which is again hard to do from Earth. So our best images of Uranus's rings come from Voyager when it visited. The rings of Neptune are similar to the rings of Uranus. They're very dark as well. They're also seen as partial rings or ring arcs. They have a sort of lumpy, brighter areas and darker areas in some of them. And that's unique to Neptune. It has 5 rings, 3 narrow and 2 wide. So those are all the rings in the outer planets. Now, it turns out rings and moons are tied closely together. Moons and rings are interconnected. So without moons, rings would not exist. Moons create structure in the rings. So in 2 ways. One, moons keep the rings confined. There's 2 ways that moons can keep the ring confined. We showed you shepherd satellites, where you have 2 little satellites on either side of a ring that hold it together. These keep ring particles in place, and without shepherd satellites, they would, spread apart and dissipate. Additionally, rings would dissipate over astronomical time scales if they're not resupplied. It's thought that the new particles for the rings come from impacts on moons. So the moons provide material for the rings. And we definitely know this is the case for Saturn's F ring because it's fed by those geysers from Enceladus. But there's another way that moons and rings interact. So shepherd rings are the simple way that define the edge of some of the rings. But also orbital resonances create structure in rings. So what happens is that if you have a larger moon with a stronger gravity, orbital periods of ring particles will be a multiple of the orbital period of a moon. So that the gravity of that moon sort of cancels out or is stable. So the moon orbits once, the ring particle orbits twice. This causes these resonances between the moon and the rings cause particles to be enhanced in some locations. Some locations get more ring particles and depleted in others. This is how you get things like the Cassini gap. The Cassini gap corresponds to a resonance with Titan, the largest moon of Saturn. And Saturn has a whole jillion moons, so there's a lot of moons to cause resonances. And actually a similar thing happens with Jupiter and the asteroid belt. There are similar resonance patterns in the asteroid belt where certain resonances lead to more concentrated asteroids and others lead to less. And it's probably why no planet ever formed in the asteroid belt region, because of resonances with Jupiter. So why do the Jovian planets have rings? All 4 Jovian planets have a ring system, as seen here. Others have particles that are smaller and darker than Saturn's. It's thought that we may just be at a top period of time where Saturn's rings are at their most impressive. And they may not last. So the particles and rings, they form from dust created at impacts on moons orbiting these planets. And how do we know this? Rings aren't a leftover from planet formation because the particles are too small to have survived this long. So the material has to come from somewhere. There needs to be a continuous replacement of tiny particles because they'll just get knocked loose and fly off. And the most likely source is impacts on the Jovian moons. There's a nice correspondence. The planet with the best rings, most impressive rings, has the most moons. The Jovian planets all have rings because they possess many small moons close in impacts on these moons are random, and Saturn's incredible rings may be an accident of time. We may be just at the right time to have super impressive rings around Saturn. So, all the rings are made of billions of tiny particles, each orbiting the planet. The ring particles interact with each other. There's gravitational interaction and collisions. It could be a shattered moon. A collision with the moon may have formed the ring particles, and any body close to the planet may have been torn apart or prevented from forming by tidal forces leading to the ring. So all of the Jovian planets have a ring system. The ring particles vary in composition. Each orbit their planet like a tiny moon, and moons interact with the rings to give them structure and to help keep the rings confined. So in summary, the outer solar system has 6 large moons, 12 medium ones, and many smaller ones. Titan has a thick atmosphere and may have flowing rivers of methane. Triton has a fractured surface and a retrograde orbit. The medium-sized moons of Saturn and Uranus are mostly made of rock and water ice. Saturn's rings are quite complex, and some are defined by shepherd moons. The Roche limit is the closest a moon can survive near a planet. Inside this limit, rings form instead. Jupiter, Uranus, and Neptune all have faint ring systems. Pluto has 5 moons, Charon, Styx, Kerberos, and Hydra. And dwarf planets beyond Neptune, including Pluto, are now known as Plutoids. So that is the end of chapter 12. I guess I could start a little bit of chapter 13. So we'll be working on chapter 13 next time. This is the limit to what will be on the test. So we're up to the point will be covered by the test. We have about 10 minutes left. I can do a little bit of chapter 13. Or the next, oh, it's not chapter 13. Sorry, it's chapters 15 and 16. We're not doing chapter 13. I forgot. So chapter 15 and 16 is about the sun. So we covered all the other stuff in the solar system. Let's talk about the biggest part, our sun. So let's start. This is the thing that everything orbits around. Let's talk about its structure. Mass-wise, it's 2 times 10 to the 33 grams, or 1 solar mass, or 2 times 10 to the 30 kilograms. Its surface temperature, so that's the temperature at the surface. It gets hotter as you go inside, is around 5,800 Kelvin, which is why it glows yellow. I mean, its peak wavelength is in the green. Its luminosity is 3.8 times 10 to the 26 watts, or 1 solar luminosity. Its radius is 3.39 times 10 to the 6 kilometers, or 1 solar radius. When we start talking about stars, we're mostly going to compare them to our sun. So we'll talk about solar masses, solar luminosities, solar radii, because these numbers are too big to think about. Its density, on average, is 1.41 grams per cubic centimeter. It's not actually all that dense on average. The core is very dense, but it's not very dense near the surface. And at the equator, it rotates once every 24.7 days. So it's spinning pretty quick. And because it's a big ball of fluid, it rotates at different speeds at different latitudes. And this actually has certain effects, ties the magnetic field of the sun up in knots, basically. So again, the mass, about 2 times 10 to the 30 kilograms. It's about 700,000 kilometers across. Its average density is, 1.4, 1,410 kilograms per cubic meter. It rotates every 25 days around the equator. 31 days are at 60 degrees latitude. 36 days at the poles. And the interior is for like 27 days. So different parts of the sun rotate at different speeds, and that has certain effects. And this is the luminosity. It's about 4 times 10 to the 26 watts, which is an enormous amount of energy, enormous amount of power. So, what is the sun made of? Well, we can study its spectrum. It's shining light on us. That light passes through the atmosphere of the sun, the outer layers of the sun, that absorbs some of the light. This lets us figure out what it's made of. The vast majority of the sun is made of hydrogen and helium. By mass, it's about 71% hydrogen, 27.1% helium. You'll find most stuff is going to be something like around 75-ish% hydrogen, 25-ish% helium. We'll get into why that is the case, but that's actually because that was the sort of the starting material of the universe. Because it turned out and what you'll see in stars is that they'll have a little bit more helium because of fusion or previous stars. But also there's things like a little bit of oxygen, a little bit of carbon. So this is less than 1%. So nitrogen, silicon, magnesium, neon, iron, sulfur. In fact, we found pretty much all the elements we can find on Earth in the sun. So Cecilia Payne-Gaspin in 1925 determined the abundances of the various things in the sun. This was a shocking discovery. It wasn't believed to be correct at the time. So here's our understanding of the interior of the sun. The center 25% or so is the core. This is the region that is hot enough and dense enough for nuclear fusion to occur. This is the powerhouse of the sun. This is the region where energy is produced by nuclear fusion. And then above this, energy from the core travels outwards. There are 2 layers above where energy is transported outwards. So above the core, immediately above the core, energy is primarily transported outwards by radiation. The core is very hot. It's emitting high energy radiation that spreads out, gets absorbed and re-emitted by various things through this radiative zone. Above that is the convective zone, where energy is primarily transferred by convection. Big currents of flowing hot plasma rising and sinking transport energy up to the surface. And at the surface, we have the photosphere, which is what we see, and then some layers above that. So this is the interior structure of the sun, and then the outer layers here are not to scale. The photosphere is about the 500-kilometer thick layer that we actually see as the surface of the sun. Above that is the chromosphere, the transition zone, and the corona, flinging out the solar wind. And I think I'll stop there for today. So you guys are free to go. We will continue this on Thursday. The test will be on Tuesday next week. It will be on chapters 8 through 12. So on the material we finished up through the moons and Plutoids and stuff. Any questions? Okay, have a nice day. I'll see you all on Thursday. Okay.